Firstly, I'd like to share a concept with you. Actually, we experience it every day. What's this? It's a field. Without a gravitational field, you even could not stand on the ground. But could you see it or touch it? No. Does it exist? Yes. Then how to demonstrate its existence? It's the force that you experience in the field could demonstrate the existence of the field. The existence of the gravitational force exerted on all of us convinces of the field on the Earth. According to Coulomb's law, the electric force exists between 2 point charges. We noted that there is no physical contact between 2 charges. Hence, the electric force is also field force. How to understand the interaction between 2 objects in such a case? How to interact with each other without the physical contact? Actually, if we put a charge into space, a field is established in space by this charge. We call it source charge. Then we put another charged particle into space. The charged particle interacts with the field that the source charge established and experiences a force exerted by the field. We call it test charge. The 2 charges interact with each other through a special matter which we call a field. The field is a type of matter, but it's invisible to our eyes. An electric field is said to exist in the region of space around the source charge. But how to detect or demonstrate the existence of the field since we could not see it or touch it? Let's put another charge, which we call a test charge, into space at some point. If the test charge could feel a force, then we could say there is an electric field at the point which the test charge is located. Therefore, the test charge is a detector of an electric field. How to define the electric field due to the source charge? Could we use the electric force on the test charge at some point to define the electric field at that point? Obviously not. Why not? Because the electric force varies with the test charge. Different charges experience the electric forces with different magnitudes and different directions at the same point. So, we must think of a way to eliminate the influence of the test charge. Hence, we define the electric field vector at a point in space as the electric force on the unit positive charge. It equals to the electric force on the test charge divided by the amount of the test charge. It can be expressed by this equation. From this equation, we can see that the direction of E at a point is the direction of the force acting on the positive test charge at the same point. Please note that E is a field produced by source charges separated from the test charge. Where there is a source charge, there is a field. The presence of the test charge is not necessary for the field to exist. The test charge just serves as a detector of the electric field. Whether the test charge is in or not, the field exists. Let's see this example. Here is an object carrying a much larger positive charge Q. The electric field is established in space. A smaller positive test charge is placed at a point in space and experiences an electric force at this point. When applying this equation to calculate the electric field, it must be assumed that the test charge is small enough that the charge distribution is unaffected. If the test charge was great enough, the charge distribution would be disturbed. Once the magnitude and the direction of the electric field are known at some point in space, the electric force exerted on any charged particle placed at that point can be calculated from this equation. But please note that the equation is valid only for a particle of charge Q, an object of zero size. From this equation, we know that if Q is positive, the force and the field are in the same direction. If Q is negative, the force and the field are in opposite directions as shown in this figure. Next, we are going to discuss how to evaluate the electric field due to some charges or charge distribution.